Good morning, everybody. So today I will be talking about part of my research on lecture video analysis and its different applications. To have an idea of what is a lecture video, right? I mean, or what is lecture video analysis in this case is we're talking about automated video analysis, basically using algorithms to try to analyze the image or the audio of a video. So it's a process where the input is going to be a lecture video and the output might change depending on what you want to do with that video. Today, I will be focusing on image-based lecture video analysis. Why lecture videos? Well, because the internet is full of them and you can find a lot of material these days, including complete lecture video recordings. You can find tutorials, you can find documentaries, you can find a lot of stuff. These have become a very useful resource for students, but also for faculty. They can be useful sometimes to find, for example, alternative explanations to important topics, like maybe you can find more examples trying to explain some hard thing, and sometimes that can help you as a student. The other advantage of lecture videos online is that they can be enhanced because it's not like a live lecture. So this can be edited and they can be modified to include some animation or stuff like that that might be helpful during the lecture. And thanks to the pandemic and the emergency remote learning, there is a ton more videos than they were ever before. And so the ones that were there already became more relevant because many people cannot attend in class person, but also we are getting more and more being recorded. So, I mean, there is like plenty of reasons to process them. So this is a lot of material basically with very limited ways to access it. The problem is you can try to find them on search engine like Google, but they don't always handle these videos properly. I mean, recently they have started processing the audio and you can maybe find stuff based on keywords on the audio transcript, but that's not enough sometimes. For example, there could be a lot of stuff that is handwritten on the whiteboard that is never said on the video that you will miss it, or you won't be able to find it if you only process the audio. So to have an idea of the type of application that we are targeting here, imagine for a moment that you are watching the lecture, the video of a lecture where the professor says something like, recall AX equals B, but you don't actually recall what's that. So if you can pause the video and select this portion of the content and say search, for example, and maybe the system comes back to you with a list of videos or portion of videos where the same formula has been written on the whiteboard from the same collection of lectures. Possibly the system can tell you, oh, this is related to systems of equations, to matrix reduction, to linear algebra. Then you can get an idea of what is this part talking about, right? So that's the type of application that we are targeting here. So before I enter into the application part, in this talk, I will be first describing some of the processes for analyzing the lecture videos, and then I will be talking about applications. So the first type of analysis that we will be looking at is the extraction of content from the videos. The first method we tried a few years ago is based on traditional image processing techniques. By the way, you can download this code. I mean, most of these works that I will be describing today are publicly available. So if you want to play with the code, you can do it. Feel free to download and try it on your own. So the idea is, given an image that looks like this, where the speaker has been written a lot of stuff on the whiteboard, we want to extract the pixels that represent the handwriting. So one idea is, what if we could say estimate what's the background? So using some image processing techniques like the median filter, we can remove the content and estimate a background image that if we subtract from the original image, we get kind of like grayscale image where the content is gonna be white and the background is gonna be black. This image is very easy to binarize and to get the content. One thing though is like depending on whether it's a whiteboard or a chalkboard, when you do the frame difference in here, it could be, I mean, darker or lighter than the background. So for whiteboards, the content is usually darker, so you need to take like the negative values, and for chalkboards, you need to take the positive values because it's lighter than the background. But I mean, if you do it right, you can get the content like this. And this is more or less the first idea that we tried, using a combination of machine learning and this image processing to get a binary version of the image. Now, the problem here is, as you can see, the content is there, but there is a lot of extra stuff that, like, the background is there, the speaker is there. So we don't want that. We only want the handwriting. So one of the first idea was like, how about we try to find what is the whiteboard, and based on that, we cut it. We cut the content. And so that's we tried this idea using the Huff transform. It can effectively remove a lot of stuff from the background, but obviously the speaker is still gonna be on the image. So how can we remove him? In this case, what we did is a spatial-temporal analysis, trying to match the content that was in one frame and that appears again in another frame. Maybe this content can be occluded for a few frames because the speaker is like on top of it, but then it's visible again. And so we match this content, assuming that the camera is fixed. So it wouldn't work if the camera is not fixed. So because the camera is in a specific position, we can match the content on the same space through time. And that way we can tell, okay, these stable things are the handwritten content, and the unstable things, in this case, the speaker, needs to be removed. And so we detect and remove the speaker. And at the same time, we also reconstruct the image with all the content that was occluded is now visible, as you can see on this example, where you can see that the content is written and stays there despite being occluded for a moment. So this method worked fairly well, but we were trying to see if we could get better results with other more recent techniques. So the next thing we tried was using deep learning, in this case, text detectors, to try to extract the handwritten content from these videos. And so we try with deep convolutional neural nets that were originally designed for syntax detection to get this handwritten content. The problem is syntax looks quite different, especially the aspect ratios are nothing like math. When you have like a matrix on the board, or you have like a plot or stuff that we care about, and it's not visible like this. So we had to do a few modifications to those detectors. We also had to retrain them with their own data. And after that, it is able to mostly detect, I mean, a lot of the stuff that is on the whiteboard. So for an image like this, after running the detector, the output might look like this. As you can see, it's not perfect. And the problem is there is a lot of variation because the decision is made locally per every frame. So it's unstable. So just like the previous version, the binarization, we also had to look at this detection through time to try to get a stable version. So that's what we do. And after that, we can binarize the image, only getting the content that is within these regions. And then we get something that looks like this. Now, it's good to some extent because the background is not there, the speaker is not there, but a lot of the content that is occluded is still missing, right? So we apply again the same strategy to do the spatial-temporal analysis of the content, and then we can bring back some of the content that was occluded in this portion. Now, while this approach worked kind of decent, it has a few drawbacks in terms of being able to catch, I mean, content, it can have any shape. So it's kind of hard to try to encapsulate everything on boxes, right? Even if they are rotated boxes. So the next approach is still using deep learning, but more like a fully convolutional network that takes the image as input and the output is an image. So trying to do the classification at the pixel level. And we proposed the FCN-LectureNet last year that basically can do the extraction using just one network. So as you can see here, it's no longer dealing just with whiteboards, but it can also work with chalkboards. And even though there are two different types of chalkboards within the same image, it can still extract the content from both of them while removing all of the elements that are on the background and reducing the amount of noise that can be easily picked or confused with the content on the chalkboard itself. So to construct this network, we took inspiration from our earlier approach based on image processing, where we were taking the image, estimating the background, doing the subtraction, and then the binarization. We just passed that to a network architecture that looks like this. So I don't know how many of you are familiar with the idea, but this is like a UNet style network that has a down sampling pad that will process the image and code it to some features, and then a decoder that will bring it back to the original resolution with different feature maps. But then these feature maps are passed to 3 branches. The first branch is a background estimator branch. Basically, just like this idea, right? Try to estimate the background of the image, but using the network. And this background is subtracted from the input image. Then the second branch is doing a test mass prediction, like try to detect what is the text. And this is going to be binary. So the white pixels are going to be any handwritten content, for example, and everything else that is background is black. So we multiply this mask by the output of the previous one, and now we have an image that mostly contains handwriting. The next step is to binarize it to fully differentiate between background pixels and what is actually handwritten content. And turns out that this approach works fairly well. Now, there is just one problem here. This network is not so big, but not too small either. It has 15.8 million parameters, and we have only so many lecture videos, in this case 17, from which we label 169 unique keyframes. So for any of you that have the chance so far to play with neural networks, you will know that with this amount of data is far from being enough to train a network of this size. So what's the solution? We had to use transfer learning. So basically, we trained the network on different tasks to try to help it learn enough information to improve on the final task. So the first stage of pre-training that we use is based on reconstruction of images. So here we use a bigger data set, the MS COCO, that has 118,000 images. And we use this to train both the shared unit part of the architecture plus just the background estimation branch. So the input is an RGB image, and the output is going to be an RGB image that represents the median filter image. So it's not trying to reconstruct the same exact image as you will see typically on the literature. Is a different version where, you know, inspired again by the original approach, try to filter out the content. And after pre-training, the output of the branch looks like this. So this is the input, and this is the corresponding output. As you can see, it can effectively learn to predict what is part of the chalkboard in this case, and eliminate the content, basically. So if you subtract the image on the right side from the image on the left, you will basically have access to the handwritten content. Now, this is just one branch of the network. We still have the other two, right? So to train the second branch, we use transfer learning from text detection. So in this case, we use data set called LSVT, Large Scale Street View Text. It's a data set with 30,000 images from different street scenes, showing, like, you know, different type of things where there is text in English and Chinese. And we use it to train the shared part of the network, plus the background estimation branch and the test max branch as well. The input is, again, an RGB image, and the targets are still a median filter image on the background estimation branch, but the text max on the other branch. Now, this is general text. This is not handwriting, right? So it's not going to be as effective as to predict things like, or what is the handwriting on the whiteboard. Still, after just pre-training on this different data set, this is the type of outputs that we get on that branch. As you can see, it catches most of the handwritten text, but it misses a few things. It's not that smooth. There are a few false positives here and there, but it is kind of decent at trying to detect what is the text, right? So this is just pre-training, right? So the next stage, I mean, after this point, the network is ready to be trained finally on the actual data that we want to work with. That will be the lecture videos. So this is the last stage where we use on 169 images to retrain the network completely. This time is the full network being trained. The input is an RGB image, and the targets are going to be supervised on two branches, the text mask branch, but also the binary handwritten mask. We don't train the background estimator branch at this point. We let it learn whatever it thinks is useful. And we found that this works better than trying to force it to keep predicting the background, the original medium filter image. So after retraining, the background estimation branch produces something that actually looks like this. It's not what we originally thought or what we originally expect, but because of the way that the architecture works, it tries to maximize the contrast between the handwritten thing and the background. So when we have something like this, like a chalkboard with white handwriting, the pixels of the handwriting become black, and it's the opposite. If we have like a whiteboard with dark content, it becomes white pixels on the background. Basically, it's trying to maximize the contrast. So when you do the subtraction, the content is way easier to binarize, right? After retraining the text mask detection branch, we get something like this. As you can see, it's much smoother than the original version that was pre-trained with stuff from like the scene text, right? It still has a few false positives, like some point here, but it's not so bad. It captures everything on the handwriting, which is good. So when we do the subtraction, multiply the subtraction by this mask, and then apply the binarization, we obtain a very smooth image that looks like this. Basically, it's like the handwritten content that is on the whiteboard that is successfully extracted, and it's very clean in average. So far, this is the best method that we have for extraction, and we believe that if we had more data, it will become even better. So that's just one type of analysis that we can apply to the video. There are a few more things that we have to consider, like the speaker, right? How about we try to analyze the speaker, not the content? And here we made some work towards trying to identify what were the speaker actions. Again, the code is publicly available if you want to try it. So the idea is we will try to identify what is the speaker doing on the video, right? There can be a few actions like writing or erasing content, and we want to automatically identify that. And for that, we start with the pose estimator that will give us basically the pose of the speaker at different moments. So we can see where is the hand, for example, detect in which point is the back, or the arm, shoulder, all of that we can tell thanks to the pose estimation. And the idea is that we can analyze this pose through time to try to identify when is the professor writing or erasing, right? All of these patterns. So for this purpose, we basically divide the video into small segments of 15 frames. That's roughly half a second of video. And for each of these half second, we want to know what's the action of the speaker. It could be different things. So like writing, explaining, erasing. We assume that the speaker is performing only one action, or what we call the dominant action. Of course, a person can be doing several things at the same time, right? But we care about what's the most relevant towards the lecture itself. So we tried a couple of approaches to classify what's the speaker doing based on this idea. And the first one was to use traditional machine learning techniques like random forest combined with motion features to do the classification. And these motion features describe things like the joint displacement. For example, how much is the hand moving towards different frames, right? The relative displacement between frames. And then the relative distances between joints. For example, when the speaker is deleting, there's going to be a lot of like changes between the distance of the shoulder and the hand because of this motion, and we can capture that with these features. Turns out that it worked fairly well, but we still thought that it could improve. So the next thing we tried was a more general action classification approach using graph convolutional networks and a method called the 2S AGCN. The idea here is that the pose is a graph, right? Basically, the joints are like the vertex of that graph, and the edges will be like the bones. So what we want is to basically, if we represent this through time, right? Different frames, same pose, or pose is changing, and we connect also the vertices, like the same joint across time, and that forms a graph. And it's a graph classification problem. Basically, we have the entire graph for so many frames, and we want to classify this as, is the person writing, is the person leading, is the person explaining something. And it worked slightly better than the other approach, not as great as we expected. Maybe we needed more data, but it's better than the first method. So finally, the last part that we have looked at the video, I mean, try to analyze on the video, is the temporal segmentation. So there is this notion that when you are in a lecture, just like this talk, right, there are like portions where you can identify there is a change of topic, right? We change from one topic to another subtopic. Things change. In the case of, say, like a math lecture, it's very typical that maybe it's a full example that the word is, the whiteboard is gonna get like full, and then it's gonna get deleted, and some new stuff is gonna be handwritten again, and so on. So the idea is try to automatically identify those segments and split the video. And for that, well, we have proposed a few different ideas. The first one, we call it the conflict minimization. To have an idea of what we mean by this, first we need to understand what's a conflict from this perspective. So again, we are dealing with fixed camera videos, right? Imagine that there is something that gets written on the whiteboard at some time one, and it's gonna get deleted from the whiteboard at some time two. After a while, something else gets handwritten on the same space of the whiteboard at, say, time 3, and the same stuff is going to get deleted from the video at time 4. So these two, we say that are in conflict because they occupy the same space of the board. If you want to extract these two into the same segment, you won't be able to catch both, right? If you want to use just one image, you won't be able to represent both part of the content because they are on the same space, so they are in conflict. So how do we solve the conflict? If we were to cut the video anywhere in between the time where the first portion of content disappears and before the next one appears, the conflict is resolved. So what we do here is we build a signal by counting for each frame how many conflicts could we solve if we were to cut the video there. And we form a signal that looks like this. It's like the blue thing that you see here. We use the signal to greedily cut the video recursively. So in this case, the peak, the highest peak is where we cut. We select this one and we cut it, and then we have like everything before that point and everything after that point. So what do we do next? We recursively compute again the conflicts, but only for each segment. And the signal is much weaker, but we can see that there are still a few peaks, right? And so we pick the next one to split the video, and we keep doing that until either there are no conflicts or the segments that we will generate by cutting on the peaks of the signals are too short for us to care. So if that's the case, then we don't cut it. And after this, we basically have different segments of the lecture. Now, this signal here represents the estimated handwritten content on the whiteboard at different frames of the videos. And the vertical lines are the actual splits selected by the conflict minimization. Now, there is some interesting pattern here. If you see, for example, here at frame 300, you will see that the speaker is like starts writing content. That's how a typical lecture goes. The professor is maybe talking and writing. At some point, the professor might stop to explain something, and we get like a plateau. like no new content is getting written during that time, and then it starts writing again, and then maybe stop for another short explanation, and then writes again, and then some longer explanation of the entire thing, and then the professor starts reading the word, and we see how the content goes away, and the pattern repeats. That's how a typical lecture goes. Now, we don't optimize to detect these erasing events, but by doing the conflict minimization, somehow the algorithms automatically selects those points where a lot of content just got deleted and new content is about to get written. It's like the perfect point to split the video, and it's found automatically. We were not trying to find these points explicitly, right? We were just trying to minimize the conflicts. So in practice, this approach works fairly well as long as you can extract the content successfully and the video has not been edited. I mean, the next thing we tried, and since we also do the speaker action analysis, was like, how about we actually look at the times where we know the speaker is deleting stuff? And that's our second approach, the access map post, where we use those results from classification of speaker actions at every segment. And we want to identify portions where the speaker deleted a lot of stuff and try to split the video there. So obviously the classification has some issues. So we first need to clean up the results a bit. So if there are gaps between long erasing events, we close those gaps as long as the gap is not so big. We then remove any type of false positive, right? Maybe there is like a short erasing event detected in the middle of somewhere. It could be a real thing, but it could be too short for us to care. So we don't split there. So we remove those, and then we apply the same idea of, we greedily split the video based on the longest erasing events. So once again, we generate different segments of the lecture in time. While this idea actually worked better than the previous one, as long as the speaker is deleting stuff on the video. The problem is the edited videos. Like if you go to YouTube, these videos have been intentionally edited, and sometimes not even the writing events are there. It's just like content appears and disappears, things like that. So if you try to look at what the speaker is doing, you have no way to split those videos. So that's how we finally did our last approach, that is based on estimation of the deletion events. So the idea is that we don't exactly care about erasing. We don't necessarily need to look at when the speaker is deleting something explicitly. What we care is those places where the content changes a lot. So for example, a lot of stuff got erased or disappeared from the image at once, and a lot of stuff gets written right away or is gradually getting written, depending on the type of the video. So we want to capture that because the idea is that in the middle of that is the ideal deletion events, the good split points. So our idea is to use the information that we get about when content appears and disappears individually to create a signal that can be used to estimate when a lot of content disappears from the video at once, either slowly or fast. So we build a signal that accumulates how much content has been deleted on contiguous frames. And when a lot of content gets written, we reset that signal back to 0, and we keep doing this through the video. And we obtain something that looks like this. Orange here is the content that gets written on the video, and the blue is the points where a lot of content is deleted. So the green is the accumulated deletion events. So when there is a lot of content getting deleted, we get like a peak on this image. And when some new content starts getting written, then the signal is set back to 0. And the idea is, if you can detect these peaks, then you have good split points for the video. And that's what we use. And it turns out that this approach is the one that works the best because it can handle both videos, right? The ones where you can see the speaker deleting stuff slowly, or as well those that you cannot see it because it has been edited. So it works well in both cases. So that's everything that I wanted to mention in terms of the analysis of the videos themselves. So once that we have the content, the temporal segmentation, the speaker actions, what else do we want to do with the video, right? And that's where we start building our applications, right? We analyze the video, we want to do different things with it. So the first one that I'm going to talk about today is the lecture video summarization. So before we get to that, we need to understand what's a summary. I think we all know that it's when we talk about the summary of X, right? We're talking about a shorter version of X, where this shorter version keeps the most relevant bits of information from the source, right? But I don't know how many of you are familiar with this idea, but there are, generally speaking, two types of summaries that we can create. The first one is the abstractive summaries. They are called abstractive because we are creating what we know as an abstract, right? It's like, for example, you have a 10 pages long document and you read it, you understand it, and then you can rewrite it in your own words in maybe half a page or something like that. So that will be like making a short abstract, but at the same time, try to keep the most relevant information on that portion, right? That's one type of summary. Now, another less common type of summary is the extractive summary, where you still summarize it by extracting the information directly from the source. So this is more of a literal type of summarization. So instead of trying to change the content and synthesize it, you just use the same source to try to keep the most relevant bits to create that summary. Basically, try to put together a coherent summary from literal copies. And that's the type of summarization that we are attempting to do on lecture videos, an extractive summary. So you start with a lecture video that is maybe 45 minutes to 60 minutes long. And the idea is how we can create a summary that is maybe 15 to 20 frames, representing everything that appears on that lecture. Here we are dealing with a simpler case where the camera is fixed. The person is writing on whiteboard or chalkboard on the video. The videos are at least full HD quality, and there is just one structure on the video. And the input, again, is one lecture video that can be long, and the output is going to be a set of binary keyframes with all of the content that was handwritten through the lecture. We tried a few different methods for this. The first one is the one based on image processing that I described earlier, the content extraction, right? Where we do the binarization of the images, we segment the whiteboard, we do the spatial-temporal analysis to build this spatial-temporal index, and then we apply the conflict minimization that I described earlier. And using this, we basically have the content and have this portion of the videos. We use those portions of the videos to try to generate one keyframe for each of these segments. And with that, we finally get a set of keyframes. This will be like the keyframes for those 8 segments I mentioned earlier with the conflict minimization. As you can see, these are the corresponding keyframes for each of these segments. And as you can see, it's like full whiteboards with different content. Basically, every time that a lot of stuff got deleted and new stuff got written. Maybe not all of the whiteboard, but a significant portion of it. So while this method worked well, I mean, we had other ways to extract the content. So we try slightly modified approach, like how about using deep learning, right? If we have the content detection at the region level, try to do first a coarse refinement of those detections, followed by the same stability analysis and conflict minimization, and then again generate keyframes. So that idea works very similar to the previous one, but not quite, not always. So in the middle of this, we had some different idea, a couple of different approaches. One of them is, what if we try to not create keyframes, but concentrate on the regions themselves? And so basically create a summary based on key regions. So instead of trying to just get the entire frames, try to get the unique pieces of handwritten content that appear on the whiteboard. And the idea is fairly simple. So we just do the detection. We need to match those content across times, and we need to cluster. The advantage of this approach is that the camera doesn't have to be fixed because it will test matching between portion of content no matter where they appear. And then we can generate the key regions. And we presented this work in the CB workshop at ICDAR 2019, and it got the best paper award for that workshop. At the same time, we were also trying a very different approach based on speaker actions. Like I mentioned, this one is very different because it doesn't look at the content right away. It only looks at the speaker at first. And the idea is try to get as far as it can without looking at the content. So it starts with the estimation of the speaker pose, followed by the classification of the actions, using these actions to segment the video the way that I described earlier, right? Based on the times where we detect that the content is getting deleted. And with this information, try to select keyframes, which are binarized until the end. So it's inverted. The previous one start binarizing and then do the segmentation. This one starts with the speaker analysis and does the binarization until we have selected the keyframes. Now, how do we select keyframes if we haven't looked at the content yet? So we still have some information from the speaker actions and where the speaker is writing, and we kind of know the position of the hand. So based on this information, we can make some estimation of where the content should be. It's not perfect, but it works fairly well in practice. Now, extracting the keyframes can be a process. I mean, we distinguish between two cases. It can be easy at times, or it can be hard sometimes. The easy case is, for example, you detect when is the last time that the person wrote on the board, like this segment, and the time before the content gets deleted. If somewhere in between that, the speaker goes out of the image, that's like the best thing that could happen, because we get a keyframe that looks like this. There is no interruption from the speaker, and we just have the content. So that's the best case scenario, right? That's neat. We get one frame and we are done. Now, life isn't so easy always, right? So in a few cases, we cannot find such a frame. So we need to try to identify keyframes where most of the content is visible. For example, in this case, we try to pick the frame where we estimate that there is the most content visible and the least content occluded. And maybe we extract a keyframe like the one on the right side. The problem is the head of the speaker is occluding the matrix, the system of equation that is behind, and even a portion of the text. So we cannot use this to represent the entire content, right? So what we do is we do an estimation of the content that is still occluded, and we try to find another keyframe where the speaker is not occluding that part of the board. At least one, right? It could be several. If the speaker doesn't move too much, it can try to use several frames until all of the content, estimated content, has been uncovered. So in this case, it picks another frame like the one on the left. And as you can see, if we were to combine these two frames, we can easily get all of the stuff that is on the whiteboard. Again, we have information like the position of the speaker, and we have an estimation of where the content might be. So we use this information to remove the speaker from each image, combine them, and then binarize them. And that's the last part, right? Once that we have the keyframes, we create a binary image for each of the temporal segments. Whether we extracted one or more keyframes, is at the end just one binary keyframe per segment. And that's the summary of the video. So in practice, this approach works fairly well. We only had a few cases where it might be a bit noisy when, for example, the pose detector fails. Like this, only the hands of the speaker is visible on a small portion of the video, and the pose detector tells us there is no person in the video. And obviously, that's not the case. So we get a bit of noise like that. But in average, it creates better summaries than the other method, again, because it's looking at the speaker actions explicitly, as long as you can see them. So we presented this work at ICDAR 2019, and it got the best student paper award. So, I mean, it's good, but like I mentioned, the problem is if the speaker is not deleting or even writing stuff on the image, then it can get troublesome. So that's how our last approach came to be, right? This time using the FCN-LectureNet to do the content extraction, which as I show you, it can do a good job in terms of removing the speaker directly from the image and other background elements and just getting the content. Followed by the same spatial-temporal analysis to try to bring back the content that was occluded and not visible on some frames. And using the deletion event signal, then we have like the temporal segments, the content. And so the last thing is use this information to generate the keyframes. And right now, that's the best method that we have. Once again, the code is publicly available. So if you want to download it, try it, play with it, you can download it and use it. So that's just one application. I'm just gonna briefly talk about other applications that we have been working with. Based on, for example, after we get the summaries, what else can we do? We can, for example, do some advanced navigation. And let me show you briefly some demo here. Okay, so this is built with an earlier version of the method, right? Not the last one. So the keyframes don't look as clean as the previous one, but you can see that basically we have the different keyframes that were automatically extracted from the video, right? The thing is, you can use them to get a quick idea of what is written on this video. So if I want to say, go to the specific portion where this is getting explained, like when the professor wrote this C3, I can click on it and the tool can navigate me to the specific part of the video where that content is getting handwritten on the video, as you can see. So I can do it for basically any part of the handwritten content, right? I can say, go here and I want to see this R square. And it will take me to that portion because it has the spatial temporal structure that tells it when the stuff appears and disappears. So it can do this type of navigation. So this is one of the things, like one of the applications why we care to process the videos and why are we trying to do this. So the other thing that we have been trying to do is advanced search. Basically, this notion that you can index the content that you extract and you can allow people to find stuff on those videos, right? Including the handwritten math, which is typically neglected. So also, if there were some other supplementary materials, maybe try to do search between those materials and the content on the whiteboard. And so the idea is like this: maybe use a portion of the content from the whiteboard to find the same portion or similar looking portions on same or other lecture videos, or to use it to find automatically the lecture notes where the same stuff appears on those notes, or even take a portion from the notes of the class, for example, in LaTeX, and find a portion of the video where that equation is getting discussed on the lecture. Or find the same equation on different lecture notes from different classes. So all of the 4 scenarios. And for this, we propose the visual search engine called Tangent B. Basically, the idea is it can do indexing and searching of mathematical expressions, but also some text in lecture materials, including videos and supplementary materials. The way it works is based on line of sight graphs, so it doesn't recognize the math content, and that's the neat thing. It's visual search, so it's just trying to match the layout of symbols. The only thing it needs to identify are the individual symbols that appear on the image and the spatial relationships between them, and it can use those to match stuff. Again, the code is publicly available if you want to try it. Let me show you a short demo of the system. So this is how the system works. For example, you can take some LaTeX it will automatically translate that LaTeX into an image and try to do the same processing as it does on the whiteboards and use it to match content on videos where the same content appears. If you don't know why some of the content is getting matched, you can, for example, click here, the show match, and it will display to you why some of this stuff is being matched. Obviously, some are good matches, some are like decent partial matches. And same as the advanced navigation, you can click on the result and find the specific frame of the video where that specific content is getting handwritten on the whiteboard. As you can see it. So that's the goal, right? You can basically find stuff and then go to where is this content there on the video. It takes you to the specific part where the content starts getting handwritten. So yeah, that's all I have about search. So I wanted to mention we did present this work at ICTHR in 2018, and it received the best paper award on that conference. So sorry, not that one, this one. Yeah, ICFHR 2018. So the last thing I want to briefly mention here is the accessibility. It's like more like a future work that we want to do. And the idea is that lecture videos are a good resource, but not everybody can take advantage of them because of different things like how readable is the content, or is like if the person has some hearing impairment, right? So being able to automatically generate transcriptions from the video, or even being able to enhance the content. I mean, we want to look into those type of applications to try to make those videos more accessible to everybody. So with that, I'm going to conclude my talk. So as just you remarks, right, given the current situation, it has shown us that there is a need to basically speed up the development of this type of tools. No more than before, we have a lot of videos getting produced these days, and certainly we want to have ways to process them and to get the best out of them. There are a lot of applications that we can support if we can do lecture video analysis, right? And these applications can be useful not just for students, but also for teachers. And the advantage here, I mean, a good thing is like as the artificial intelligence in general improves, right, we can get better and better methods to analyze these type of videos.